Molecular clouds represent one of the most fascinating and crucial elements of the interstellar medium, playing a fundamental role in the birth of stars and the evolution of galaxies. These remarkable cosmic structures merit detailed examination to fully appreciate their significance in astronomical processes. Molecular clouds are distinct regions within the interstellar medium, characterized by their unique density and composition. These vast assemblages of gas and dust are sometimes referred to as stellar nurseries, when star formation occurs within them, highlighting their crucial role in stellar birth processes. Unlike other areas of interstellar space predominantly containing ionized gas, molecular clouds possess sufficient density and size to permit the formation of molecules, particularly molecular hydrogen, H2, and enable the development of H2 regions. These structures constitute approximately 50% of the total interstellar gas within a galaxy, making them substantial components of galactic architecture. The interstellar medium density in molecular clouds typically ranges from 10 to 30 particles per cubic centimeter, which represents a concentration significantly higher than the average density in the solar vicinity of approximately 1 particle per cubic centimeter. This enhanced density creates the necessary conditions for molecular formation and subsequent star birth processes. The chemical makeup of molecular clouds presents a complex and dynamic profile that astronomers study using various observational techniques. Molecular hydrogen, H2, dominates the composition of molecular clouds, constituting their primary gas component, with carbon monoxide, CO, representing the second most abundant compound. The detection of molecular hydrogen presents significant challenges for astronomers due to observational difficulties in infrared and radio wavelengths, leading scientists to frequently utilize carbon monoxide as a proxy indicator for H2 presence. This methodological approach relies on the assumption that the ratio between CO luminosity and H2 mass remains relatively constant, although this presumption has been questioned in observations of some other galaxies. Beyond these predominant molecules, interstellar clouds contain a remarkable diversity of chemical compounds. Researchers have identified larger molecules, including methanol, ethanol, and complex structures such as benzene rings and their hydride derivatives within molecular clouds. Perhaps most surprisingly, polycyclic aromatic hydrocarbons, large organic molecules comprising multiple aromatic rings, have also been detected in these cosmic environments. The comprehensive chemical examination of interstellar clouds involves studying the electromagnetic radiation they emit across the spectrum, from radio waves to gamma rays, allowing astronomers to map molecular abundances throughout these structures. The structural organization of molecular clouds reveals intricate patterns characterized by irregularity and filamentary arrangements. What appears visually as the boundary of a molecular cloud actually represents a transition zone where molecular gas transforms into atomic gas through rapid processes, forming envelopes that create the impression of defined edges to these cosmic structures. Within the broader molecular cloud formation, the density distribution demonstrates significant fragmentation that astronomers categorize into distinct substructures. Clumps represent larger substructures averaging approximately 1 parsec in size and function as precursors to star clusters, though not every clump will ultimately evolve into stellar formations. Cores constitute much smaller, denser regions, roughly 1/10 the size of clumps, that demonstrate gravitational binding and undergo collapse during star formation processes. Perhaps most significantly, filaments have emerged as truly ubiquitous features within molecular clouds. These dense molecular filaments fragment into gravitationally bound cores that typically evolve into stars. Research has revealed that continuous gas accretion, geometric bending, and magnetic field interactions may govern the detailed fragmentation patterns of these filaments. Giant molecular clouds, GMCs, represent the most massive assemblages of molecular gas, containing more than 10,000 times the Sun's mass. These enormous structures span between 15 to 600 light-years in diameter, with typical masses ranging from 10,000 to 10 million solar masses. Despite the Sun's greater density compared to GMCs, the sheer volume of giant molecular clouds results in substantially greater total mass. The internal structure of GMCs exhibits complex patterns including filaments, sheets, bubbles, and irregularly shaped clumps. The densest regions within these filaments and clumps, termed molecular cores, exhibit densities exceeding 104 to 106 particles per cubic centimeter and are frequently studied using ammonia as a tracer molecule. The significant dust concentration within molecular cores typically blocks light from background stars, causing them to appear as dark nebulae when viewed in silhouette. In contrast to these massive formations, smaller molecular structures called Bok globules represent isolated gravitationally bound small molecular clouds with masses less than a few hundred times that of the Sun. Additionally, a distinctive type of diffuse molecular cloud was identified by IRAS in 1984, characterized by diffuse filamentary structures visible at high galactic latitudes with typical densities of 30 particles per cubic centimeter. The life cycle of molecular clouds involves continual assembly and destruction processes that maintain a cosmic equilibrium. Considering their relatively brief astronomical lifespan of approximately 10 million years, molecular clouds undergo constant reformation throughout galaxies. By calculating galactic star formation rates, astronomers estimate approximately 150 solar masses of gas assemble into molecular clouds in the Milky Way each year. Two primary mechanisms have been proposed for molecular cloud formation: cloud growth through collision and gravitational instability in the galactic gas layer. Mathematical modeling suggests gravitational instability likely represents the dominant formation mechanism, as collision theory would require timescales exceeding the typical lifespan of molecular clouds. Once sufficient mass accumulates, the densest regions begin collapsing under gravity, initiating star-forming clusters in a process that ultimately leads to cloud destruction. The star formation process itself involves the collapse of the densest molecular cloud regions, which subsequently fragment into smaller clumps that aggregate additional interstellar material through gravitational contraction. This process continues until temperatures reach the threshold for hydrogen fusion, generating sufficient heat to establish hydrostatic equilibrium and forming protostars that continue gathering surrounding gas and dust. The interrelationship between molecular clouds and star formation appears consistently across astronomical observations, with studies revealing correlations between molecular gas and star formation rates from galactic to sub-kiloparsec scales. Molecular clouds constitute indispensable components of galactic ecosystems, serving as the birthplaces of stars and participating in complex chemical and physical processes that shape universal evolution. Their intricate structures, diverse chemical compositions, and dynamic life cycles offer astronomers critical insights into stellar birth mechanisms and galactic development patterns. Understanding molecular clouds more completely will remain a central focus of astronomical research as we continue exploring the fundamental processes that govern our cosmic environment.